Hello, welcome back to 61C. It's a brand new module on dependability. It's a fairly short module, and we are going to just touch on it. Remember our early story about 6 great ideas in computer architecture. So we have talked about the layers of abstraction that enable us to build these complex systems out of many components. And we do that by layering many layers of abstraction. We have talked about Moore's law that enabled us to integrate so many devices and build these complex systems. We have talked about principle of locality and memory hierarchy that enabled us to build these memory systems that look infinitely fast and infinitely big. We have talked about parallelism as a way to improve the performance in power limited regime. We have also throughout the course talked about these concepts of performance measurement and improvements, primarily through the iron law of compute and average memory access times. But we haven't talked about the 6th great idea, which is dependability via redundancy. So that's what we are going to cover now. And why is that important? Well, we rely on our compute systems more and more in everyday life and in domains that are just not purely computing. All our financial transactions are performed by computers. We drive a collection of computers. Many people's lives are supported by some sort of a computer. So we really need to care about that dependability. But the fact is that the computers fail. They might fail transiently, and we have seen before, I'm afraid, these blue screens of death and many other failure modes for computers. Often, after a computer crashes, it can come back, and we'll call that a transient mode of failure. This failure may happen because of a bad code. Well, somebody, it's not just students who forget to clean the exit functions. Production software does that sometimes as well. They do, send you a new release and it works better. But these things happen. But sometimes these failures, transient failures, happen because something did not go quite right in the hardware. Hardware made an error. If these errors persist, something really fails permanently in a computer, then often we discard them or we try to repair them if they are repairable. So in this module, we are going to spend some time talking about how do we mitigate these hardware failures by using redundant components. So we have briefly touched on that early on in the introductory module, when we can use redundancy to replace a failing part of a system. This redundancy is often encountered in memory systems. We have spare stuff in memories. But in parallel computers, we may have a spare processor core. You'll find out that on the market you can buy now 8-core GPUs or 7-core GPUs. Well, when you look at the chip, they're exactly the same, except that 8-core was disabled and they'll sell you that chip a little bit cheaper. Why was it disabled? Because it was no good, it was failing. But that's okay, you just have a little bit less of a performance. You have 7 instead of 8, and you're willing to pay less for that. So the way how it works is that you'll have multiple replicas of hardware, and there'll be some kind of a voting mechanism where 2 out of 3 perhaps will agree that 1 plus 1 is equal to 2. And you'll take that as an answer. This is made a lot easier by the advances in transistor integration densities. So we can have more of these components. Now there is another catch there. As the components are smaller, as the transistors are smaller, they have a tendency, to more frequently fail. But that is not increasing at the failure rate is not increasing at the speed at which we can integrate more of them, so we can add redundancy. The other way how we can improve things, how we can mitigate these transient failures, is through another form of redundancy. We can things can temporarily go out, and we can still continue computing without them. For example, at the very top level, the data center may go out. I mean, there may be a hurricane on the East Coast. The power may be out, internet may be out, data center goes out, the weather system goes away, data center is back up. The other thing that we have encountered is often we use these arrays of disks. If a mechanical disk fails, it's okay, because there is a way to cover for that disk by having redundancy on the shelf. So a shelf of disks will have spares. And finally, we can use a particular type of coding to add redundancy to our DRAM. So our DRAM chip, this is a DIMM that goes into computers. If you look at it, it has 9 memory chips that correspond to 9 bits instead of 8. And the reason for that is that the 9th one is there to represent parity. And that parity is going to be used to indicate if something went wrong. So, we're going to take a quick break now, and then we're going to take a look at how do we measure dependability. See you after a quick break.